Okay, welcome everybody to today's webinar. As I mentioned earlier, my name is Jill Browning and I will be your moderator for today's webinar, Toolbox for Water Treatment in Remediation Projects. Before we get into our presentation today, I do have just a couple quick housekeeping slides to go over. First of all, hopefully you should be able to hear me speak right now, but I do want to mention that if for any reason that you do have any audio difficulties throughout today's webinar, there are two different ways to connect to the audio. You can use either your computer or there is a phone number to call in as well. So feel free to switch back and forth should you have any issues through the system today. And then also just wanted to mention that due to the large number of attendees that we have on our presentation today, we have gone ahead and muted everybody's phone lines, but no worries on that. We do want to make this still as interactive as possible. So there is a way to interact with our speaker. In terms of interacting with today's presenter, you can ask your questions via the questions panel at any time throughout the webinar. And then at the end of the presentation, we do have some allotted time for questions for our speaker to answer them. So feel free to ask any questions that come to mind, and we will try to get through as many of those questions at the end of the main presentation as time allows. Additionally, we have gone ahead and made available our collection of on-demand webinars that we've conducted over the last couple years. You can access more than 50 on-demand webinars over at www.veoliawatertech.com. So feel free to go over to our website at any time and browse the different topics that are available to see if any of those are of interest to you. One other housekeeping note is we are offering a PDF participation certificate that will be made available to you at the conclusion of today's webinar. And you should receive that within 24 hours or so at the end of the webinar today. And then we do have a quick survey that we are asking or requesting your feedback for at the conclusion of today's webinar as well. It should take no more than 20 or 30 seconds. And for those of you who do complete that survey, you'll be entered into a drawing for a chance to win a $25 Amazon gift card. So please fill that out. And if you are the lucky winner, we will follow up with you directly after the webinar today. Okay, just one more quick slide that I have before I introduce our speaker today. Veolia Water Technologies, we are the leading company within water. We focus our efforts within three key main areas. Technologies, we offer advanced and robust water treatment technologies. We have a large portfolio of over 350 proprietary technologies that we're able to offer to our clients. In addition to our technologies, we are able to pair those technologies in terms of developing projects for our customers and also put multiple technologies together to meet required treatment specifications of the client. And then lastly, we have a very thorough service offering that we can provide, whether it's during projects or after. Okay, so now I'd like to introduce our speaker for today's presentation. Marc Laliberté is a principal process engineer with Veolia Water Technologies Canada office. He has more than 35 years of experience in water treatment in mining, metallurgy, and heavy industry in general. He specializes in issues of water quality and quantity, treatment of industrial wastewater, treatment of makeup water, and water management in general. And he has focused in the last 10 years in merging seamlessly chemical and biological treatment processes. So without further ado, I'd like to turn it over to Marc for today's presentation.
Good day to you all. So today we're going to be discussing about remediation. We're going to be mostly looking at case studies I believe that case study are probably the best way to present what should be done and what the way to do it. We're going to have over a short intro why talk about water when talking about remediation. The presentation should last about 30 minutes or so, so we should have time at the end, as Jill mentioned, to answer questions. If you have any questions, my email address is at the end of the presentation, so if you've got any further questions, don't hesitate to get in touch with me, and then I'll try to answer your question as best as possible. So, why talk about water treatment in remediation? First, what is remediation? You're probably all aware of that. Remediation, it's the process of returning a contaminated site to a state where it can be reused. Not necessarily the original use, but some use. Obviously, with that kind of definition, the nature of the contamination can be extremely varied. It can be basically almost anything. Usually when we're talking about remediation, we're talking about ground remediation, soil remediation. But so why talk about water treatment in remediation? It's because in our climate, when we try to deal with soil, when we do excavation, we usually, as you see on the picture actually on the right, we usually end up with water, and that water will pick up a lot of the contaminants there is on the side, so will need to be treated before it is released into the environment. One specific issue with remediation is that remediation is usually not a long-term activity. Remediation is something that you do at the end of an activity, usually, but not always industrial activity. You go there, you do remediation. After that, the state can be reused, and so you have to leave. Usually, when we talk about remediation and water treatment, we'll be thinking about something that is mobile. Not necessarily for a week, but it shouldn't usually be there for like 5 or 10 years or anything like that. So that's one of the special constraints we have when we talk about remediation. Further, and this is very general, it's actually true to any water treatment issue. Obviously, before we talk about remediation or any kind of water treatment design, we need to have a clear idea what are the discharge criteria. Those can vary a lot in remediation jobs, between fairly easy if you're in the town or a municipality which has a treatment system, you can discharge to sewer. Usually the criteria are not very difficult, to extremely stringent chronic toxicity criteria when you're a pristine Arctic environment or anything like that. Obviously, flow rate is also important. The case study that we're going to present there are between 500 and 10,000 cubic meter per day. Below 500 cubic meter per day, usually you should consider batch treatment. Batch treatment is possible, but we will not present that today. Above 10,000, it becomes difficult to have a mobile solution, a wheel solution. So usually either you need to consider to have multiple trains in parallel, or to consider a permanent installation. Obviously, for permanent installation, we can go at much higher flow than 10,000. But that's about the range where it's the sweet spot, if you want, of the treatment system that we're going to be presenting today. As I was saying earlier, contamination can be any kind of thing. If you look at the picture on the right with that abandoned building, you will notice there are tanks there, a fair number. Then this is probably a chemical process. What was in the tank exactly? Probably some organic material. It probably leak in the ground at that point. So when we're going to start digging, we're going to find all kind of stuff. Usually what we find is fairly heavy organic material, because light material will have either evaporated or migrated with the water on the ground. We often see fuel, oil, and all kind of combination. But often we'll see stuff like polyaromatic hydrocarbon, the PH, volatile organic compound. not the light stuff. The light stuff, as I said, will have migrated or evaporated, but the heavier stuff, parent polyfluoroalkyl compound, the PFAS, we are probably, well, they probably have been there for decades, but we are looking for them now, and we find them more and more because those things are not biodegradable. They stay in the ground, so we see them more and more and more. Very often, the organic will be characterized by high COD, so high chemical oxygen demand, low biological oxygen demand, which means that the organic contaminants will not be easily biodegraded, and that kind of kill the option of doing biological treatment for mobile systems used in bioremediation. Usually, it doesn't work because the BOD is too low. Inorganics, any metal you can think of, we've found into remediation site. Heavy metals like zinc, copper, arsenic, lighter metals like iron, like aluminum, all of those are typical and will be fine in many different sites. We'll have suspended solids. Obviously, you have construction activity going on at the site. You've got heavy machinery, so obviously all of that is steering the soil. So you can have huge TSS loads, and obviously pH, depending what was the activity on the site, or if you're on a mine site, if you had acid mine drainage, you can have actually fairly low pH to deal with. So how do we deal with this blend of contaminants there? Well, as I said earlier, we'll normally try to go with wheeled unit. We'll use our active flow technology, which is a sand ballasted clarification for TSS and metal removal. Usually that will mean that we need to have some kind of reactor where we can have pH change and then sludge circulation to do metal precipitation. Obviously, the optimal pH depends on what metal we're removing. Coagulant is usually used very often iron based, so like ferric sulfate or something like that. Sometimes aluminum based. It really depends on what we have to remove. Polymer can be varied. Usually it's an anionic polymer. Sometimes we'll go with the cationic polymer. This filter will be used very often for polishing. This filter basically just remove 80% of the TSS going out of the active flow. So because the relation for metals usually are in total metal, so if we remove 80% of the TSS going out of the active flow, we're removing 80% of the metals. Activated carbon for organic removal. Again, as I said earlier, we cannot really do biological reactors for those kind of jobs. The activated biological treatment, I mean, is not very, it's usually big plants. The kinetics are low because we're looking at AV stuff, so it doesn't make sense. GAC filters, so granular activated carbon filters work very well for small flow. We use ActiCarb, which is a combination of the ActiFlow with powdered activated carbon for larger flow. That actually works very well. We'll be presenting one of the case study for that. And usually we've got some kind of pH correction. Not always. Sometimes the pH of the water coming in is within range, but very often there will be some kind of pH correction. This seems simple, but actually it is quite polyvalent. There's a lot of stuff we can do. We can switch the sequence. We can play with pH. We can play with dosage of activated carbon. I thought at that stage, the best thing would be to start looking at case study to show you how we actually do this thing. So first case, it's going to be dredging of a contaminated harbor. I'm not naming sites into this presentation, but obviously you will probably recognize some of the case study there. So this is Hamilton Harbor. This Hamilton Harbor is Hamilton and Ontario is an old well, old town, not that old, but I mean in There's been industry in the area since the mid 19th century, and there's been a lot of heavy industry in there: coal gasification, petroleum refining, steel making. Actually, U.S. Steel is still there. Municipal waste, sewage, drainage, and everything. All of that went into the harbor and has basically accumulated into some kind of crud, some kind of sediment that is in. You see a sample at the bottom right of the slide that has accumulated at the bottom of the harbor. The harbor is currently being dredged, and all the sediment are going to be removed. But as you dredge, if you're familiar with dredging actually is kind of a vacuum system. You're sucking the sludge out, but when you do that, you actually entrain a lot of water with that. That water obviously pick up some of the contaminants. We need to treat that water before we discharge back into Lake Ontario. So that's what we've been hired to do. Our approach was to go with a two-stage system, removal of TSS and metals using ActiveFlow, and I'll show you a flow sheet on the next slide. So basically, it's pH control to have optimal, a lot of copper in the water, so we're looking at slightly alkaline pH. Coagulant. In this case, we're actually using both aluminum and iron coagulant, aluminum first and then iron next. And then removal of all the pH and the organics using the ActiCarb. All of that is done inside. This is really a temporary job. So the building that we have is really a temporary building. You see a picture of both the inside and the outside of the building at the back of the slide. The building is not insulated because there's no dredging in winter. So basically in winter, there is no operation, but it's a temporary building that has been put up there. And then once the dredging is finished, it should finish normally this year, will be simply taken out. And then basically at the end of the day, there will be a couple concrete pads and that's it. There will be nothing else left into the system. So flow sheet, basically, you should be able to see my cursor there, I hope. But anyway, we have the water go into something called the engineered containment facility. That's not by us, by the way, but that's where the dredging water go. From there, we pump it, go into the first stage ActiveFlow, where, as I said, we add coagulant and polymer, and then we do metal removal. And then go into second stage ActiCarb, where we add the packed powdered activated carbon, and then we add basically a reactor followed by another ActiveFlow where we remove the activated carbon. The activated carbon, once it's spent, goes back into the first stage, and then from there, all the sludge, so all the spent pack and the spent, the TSS, coming from the water, are sent back into the ECF, the Engineered Containment Facility. So fairly simple, excellent results, however, and I'm going to show you 3 different results. Sorry about that. Metals first. We have on that specific site thousands of data. So in order to better show, I'm showing you the average in the 98th percentile. What is in, you see the discharge limit on the third column. What is with the orange background and bold red is exceed the discharge limit. So we can see that the raw water actually was fairly contaminated. On average, we add too much aluminum, too much iron, too much zinc, and at the 98th percentile, we're out of compliance for everything. You can see actually that the treated water, the effluent for metal, we have excellent results. We usually have something like 2 log removal for most metals. In even the 98th percentile, we're way below the criteria. So those are excellent results, and those, as I say, are based on 3 years of data, thousands of data points. So this is something we're very, very confident. Metals were not the main contaminant into that site. Organics are actually, especially with the coal gasification industry that was on site earlier. those are all pH. There are more in that, but I mean, I selected the one where we had the most exceedance. So you can see that the raw water actually exceed all of those parameters. Again, you see that we have excellent results in the treated water. We are removing, again, about two order of magnitude for the contaminants. One of the issue we have here actually is that it's difficult to know how good we are because we have detection limit issues. So you see that for some parameters like chrysine as an example, the average and the 98th percentile is the same. It's because we're below detection limit for all our samples. So we are probably better than two-log removal for those things. I can see that our client was really impressed with the performance for removal for the pH. This was the main concern when we started this project there. Those organics are extremely toxic, and there was a lot of worry that we would have issues with that, but actually we have excellent results. Finally, the perfluoro components. This is not something that is regulated into this project, so we don't have a criteria, but we were kind of curious to see what will be the performance of the system with respect to all the perfluoro alkyl substance, spare and polyfluoro alkyl substance. Yep. This is based on a more limited number of samples there, probably in 10 samples or so, 8 sample or 10 sample, I can't recall. So you've got the raw water and you've got the treated water. That was interesting because we found that actually, even if the plant was not designed for PFAS or PFOS substances removal, we actually are removing quite a lot of the perfluoro organics. And it's actually a combination of both the coagulation in the first active flow and the activated carbon into the active carb system downstream. So that concludes my first case study. Second case study there, it's a completely different project, a completely different industry. It's an abandoned mine. That mine was once the largest lead mine into the world. The mine owner went bankrupt and left behind millions of tons of tailings and waste rock. The water is extremely highly contaminated with zinc and iron. Zinc typically concentration is between 30 and 50 ppm, which is you're way in the toxic zone for trout. At those level, I mean, it is extremely high. Iron is high, not as high as zinc, but it's also very low. pH is low. Depending on the site is not homogeneous. There are a number of pits there. Some of pits it's not too bad, but some pits their pH is like 2.5. That was kind of weird there because at that point it is remediation. The site remediation is planned and has been planned for a while. We were asked to provide a temporary water treatment plant. So, but in this case, I put temporary into quotes because what is temporary for me is maybe not temporary for others. In this case, temporary was we need to be there for at least 10 years while the site remediation is planned and take place. So it's actually kind of semi-permanent. But the trick is it is in a very, very remote location and we needed to deploy extremely fast. We had 4 months to deploy between the reception of the order and the start of treatment. And that actually here was the challenge in there. The treatment by itself, treatment of zinc and iron is fairly straightforward, but really in this case, what we needed to know is really get there and get there fast. So our approach there was to go with pre-engineered active flow, again, the settlers and reactors. Those are a very, very compact footprint. They don't require civil works. That actually save a lot. We were able to actually use the foundation of the old mill building. So we had something that was reasonably level and then reasonably solid. So no civil works. That actually really helped on the schedule. And anything else that we've looked at, actually, we had issues with foundation. We have a temporary building. Again, we'll see there temporary. It's not that temporary. I've got a picture 2 slides down. It's seasonal operation because it is an abandoned site in winter. There is no operation. There's nothing. Basically, no water is flowing. So we're just only operating during the warm season. And we were lucky enough to be able to get water tested. And then when we came there, like I said, as I said earlier, we were with an extremely tight schedule, but because we received water, we're able to test the water in the lab. We were able to find the optimal conditions, and then when we went there, and then we started treating, we knew exactly what we're doing. We knew which region to use, what concentration, what pH, and we were able within a week to start treating and prevent any overflow into the environment. Treatment system is simpler than the previous case study. So basically, it's 2 reactors in series, just to give us retention time and an active flow. There is nothing. There is no organic component there. It is a metal mine, so there's nothing. It was done with lime is the alkali there, so the little difference there for the lime addition there, but it's fairly straightforward. We have sludge circulation taking place, so as we usually do for metal removal, so fairly straightforward. We're showing only one train on this thing, but to get the capacity, that was a system where we need to have actually 2 identical trains in parallel. And I lost my cursor. There it is. Sorry. So you can see the building. The building is that white thing there. It is a temporary building. You can also see the inside. That building, even if it's seasonal operation, is actually insulated because of the remote location of the site. Even for seasonal operation, we wanted to protect the equipment inside and make sure that we don't have freezing, because in May and September you can actually get nights at -10, -15, and at that point we start to have pipe freezing issue. You can see inside on the slide on the right there that the equipment is extremely close together. As I said, we wanted to take advantage of the foundation of the mill building, the old mill building. So we were kind of constrained into the footprint we had. So we really had to squeeze the equipment. Honestly, usually we try to have a little bit more space because it makes maintenance more difficult. But in this case, what was important is to make sure that this thing was going up fast and we're able to treat the water. At the end of the day, we were treating water in mid-September, which was actually excellent, knowing that we got the order to start on this in May. And remediation is still proceeding, so we're still treating water. That site hopefully will be closed sometime in the late 2020s. I'm not sure. That thing has been in operation since 2014, so it's been 6 years. I think that the 10 years of temporary operation might actually stretch to 15, but anyway, it's been working great, and actually we've been on spec since startup. That concludes that second case study. I'll go to the third case study now. Again, very different application. This is a derailment cleanup. So we are in a pristine area in Northern Ontario. Not allowed to say more, but it's in Northern Ontario. Years ago, a train carrying zinc and copper concentrate derailed and then spill tons of the zinc and copper concentrate. It is a very marshy area, a lot of water. The concentrate got actually spilled in the marsh, And then the marsh got extremely heavily contaminated. The ore is actually a sulfide, and obviously, if you have a sulfide ore and you combine water and you combine oxygen, you will get oxidation. So you have copper and zinc that got into the marsh, and then it migrated, got into the land around, got picked up by plants, and eventually started. There is a little river that is a couple hundred meters from the site of the derailment. Eventually, the contamination plume started to reach the river, and then it was decided to do a decontamination. It's another very remote locations. They're not always are like Hamilton is not a remote location, but very often remediation jobs are in remote location. One constraint we have is that because this is a pristine area, we were not allowed to cut any trees. We had to actually work on the old rail bed, and we had maybe 10 meters wide to set up all the equipment. So as you can see on the slide to the bottom left, and on the next slide, which I'm going to show you right now, we had to actually we had to lay out all the equipment there one behind the other in a long line of equipment, because there was simply no space to do otherwise. That's also seasonal treatment. That one had no building at all. Everything was located outside. During fall, when we shut down the system, we simply drained everything and then restarted in spring. That lasted 2 summers. It is completed right now. It's no longer there, but it was, yeah. We had a couple trailers for the operators but everything else was located outside. The approach in this case is, again, removal metal and TSS using active flow. So again, pH control, sludge circulation to control metal removal, polishing using this filter. That project has very stringent metal limits also. And we had a GAC filter actually to remove organometal. One of the interesting things is that even if the original ore did not contain any organic material, because the ore concentrate was actually left into the marsh for probably 2 decades, something like that. A fraction of the metals actually got picked up and got transformed as organometals, sorry, and then those organometals are not easily removed by precipitation under alkaline conditions. They're really very easily removed by using GAC. So the GAC was there to do a final polishing of the system. Flow sheet again. So you'll see actually it's 2 pages, but basically the first page is reactor with active flow. We have, in this case, we had the sludge handling system. We don't always have. That's something that need to be established case by case. Sometimes the client will deal with the sludge. Sometimes, like Hamilton, we send actually the sludge back into the engineered containment facility. In this case, it's a simple system with a sludge tank and then cationic polymer and geotubes, so nothing very fancy, but it actually worked very well. And then on the next page, pH correction and GAC filters, and then everything was returned back into the environment. Results, as I said, metals and everything. We don't have quite as many results, so I'm talking about the 95th instead of the 98th percentile, but it still gives you a very good idea. TSS were actually very high. You can see on average 230, maximum 1400, and then we were treating down to about 1 ppm of TSS. Aluminum went from 26, those are microgram, by the way. All the metals are microgram, the TSS is in milligram. Aluminum from 2600 to 5900 in the raw water, and then went about to 3040 ppb. It's actually very low for metals, and that's actually aluminum was one of the metal where the GAC filter helped a lot there. Copper You can see the results in zinc. So again, very good results. Those are ppb levels, so we get the copper down to 1 on the 95th percentile at 0.5, and on median, and zinc to 10 or 14. Excellent results in there. We had another client that was very happy of the performance of our system there. That system, that the decontamination, the remediation has been completed, and it's been a very successful exercise there. So conclusions. Basically, each project is different, and I presented today 3 different case studies and 3 very different environment, very contexts. Each project is different. We need to have a good project definition. It is important that we sit down together, and that's the next point, sit down together and then try to understand what are the limits of the scope, who should be doing what are the constraints, why should, and all of that. And if we can do that, actually, if we can sit down together and then define together what we're going to be doing, we actually have a very good chance of making the project a success. We love complex chemistry problems. This is really what Veolia does well, and this is where we really shine. And with that, I'll pass the floor back to Jill.
Great. Thank you very much, Mark, for that very informative presentation. Before we open up the Q&A session, I just want to remind you, feel free to type in any questions over to the right-hand side in the questions panel, and we will try to get to as many of those as possible. And then one other thing that I wanted to make note of, I forgot to mention at the beginning of today's webinar, is the webinar today has been recorded, so you will get an email that will come out within 24 hours or so of the recorded presentation as well for future reference. So with that, I will open up the Q&A session. Mark, one of the questions that we've got is regarding ActiFlow. Can ActiFlow remove multiple contaminants in the same unit, such as, say, TSS, PFAS, metals, and so on?
The answer is yes, we can remove multiple components, but we cannot remove everything at the same time, in the sense that there are some classes of say some metals, like I'm going to give an example. Copper, cobalt, nickel, and zinc, as an example, are removed under about the same conditions. So if I design my system to remove one, I'm probably going to be removing all of the others. However, PFAS, as another example, are not quite designed to be removed the same way, or other metals like molybdenum and vanadium, as an example, they're removed at a much lower pH. So yes, I can remove multiple components in one stage, but depending on what I have in the water, I may have actually to have 2. I've never actually seen 3, but we could conceivably have a 3-stage. Usually it's 1 or 2 stages into the removal.
Great. Another question, staying along the ActiFlow theme here, is how does the ActiFlow process handle fluctuations and changes in the raw water composition, which you typically experience in remediating a pond, or such as like an old mine site pond, for instance?
That's actually a very good question. TSS variation are usually quite easy to handle. One of the ActiFlow, as I said earlier, is a sand ballasted clarification process. So you've got a lot of sand in the water, and you will typically have 20,000 ppm of sand in the reactor itself, and that sand is used as the ballast. If the water coming in change, say from 500 to 2,000 milligram per liter in TSS, compared to the 15 to 20,000, it doesn't really make much difference. So the active flow actually is very resistant to changes in TSS. Where it does require to readjust is if there is a qualitative change into the water quality. So you are not used to see, I don't know, nickel into the water, and then suddenly you've got a new source of water coming in, and that source is very rich in nickel. I may have to tweak my pH and my coagulant dosage and maybe go with sulfide precipitation. I don't know to do that. So that is more of a challenge. But even then, because of the retention time, the active flow is so low. Usually within half an hour to an hour, I can go back to a normal operation. So it's not that much the change in concentration that is a problem. It's a qualitative change. Something, so at some point in time, something new is present in the water, and then that changes the chemistry of the system.
Great. Another question here that came in is it important to keep a certain level of TSS in the MPR to treat water with iron, phosphate, and arsenic? And I can repeat that again. I messed that up a little bit.
I'm not sure. No.
Yeah, I will repeat that one for you. Is it important to keep a certain level of TSS in the MPR to treat water with iron, phosphate, and arsenic?
Not really. The system as it is designed, as we use it, is actually fairly flexible. We can adjust it. Obviously, as I said, we do try when we have kind of like phosphorus removal, as an example, is a case where we do try to have sludge circulation as much as possible. The reason why we do try to have sludge circulation is that it improves significantly the removal efficiency. But when we do sludge removal, that means that we're artificially building up the concentration inside the reactor. So even if the concentration in the influent water is low, what we'll do then is we'll simply increase the recirculation. If the concentration becomes higher, we'll simply decrease the sludge recirculation. So with the sludge recirculation, we're making sure that the condition in the reactor stay optimal for removal, whatever is happening in the influent.
Okay, a question regarding sludge, talking about how much concentrate you end up with on average. For example, volume per cubic meter of treated water. And then also, did you cycle that through again, or how did you manage the concentrate?
The active flow process as such produce fairly thin sludge. Usually we'll be producing 5%, maybe would be a typical value. So 5% of your influent is going to be in the sludge. The concentration obviously depends on how much you added you are. But say the concentration is going to be 20 times higher than what you have in your influent. So if you have, I don't know, 500 ppm of TSS in your water, then basically the sludge will have 20 times higher, so we'll have 10,000 ppm sludge, which is a very thin sludge. We're talking there at that point of 1% solid, then that would be a fairly typical value. However, we can fairly easily treat the sludge to increase its solid content. As I said earlier in one of the slides, actually in the slide for the case study 3, it's something that is very project dependent. Sometimes the client has a way to deal with the sludge. Maybe there's already a pond or something. If not, what we do for remediation most often is that we'll use geotubes, because geotubes for a temporary application, it's labor intensive, it does require space, but it is very efficient. And then with geotubes, depending how many you have in parallel and how long you let them drain before you decide that you need to remove and replace them, you will easily end up at, or depending if it's organic or inorganic, call it 15 to 20 a little bit on the lower side if you're organic material, a little bit maybe on the higher side if you're the stuff to dry, and that would be pretty typical. Obviously, for permanent system, we can go with higher solid content, we can go with centrifuge, we can go with filter press, and then we can go up to 40-50% solids, but it's not really applicable for kind of a remediation site where we're there only for a couple of months, maybe a year or two, and then we need to leave. Those equipment are too expensive, too complex to operate in that context. Not sure if
Great.
I answered the question, but.
Thanks, Mark. I think we've got time for maybe one or two more questions here before we have to conclude the webinar today. So we'll try to get through those. Mark, can you give us an idea, and I assume this is talking regarding the active flow as well, but can you give us an idea of the flow rates or daily volumes that can be treated by the systems?
As I said earlier, the system I presented today are optimal between 500 and 10,000 cubic meter per day. For American people, that would be roughly, I don't know, 200 to 2,000 GPM, something like that. We can do more, we can do less. Less, usually it's better to go batch treatment, which is possible, but I didn't present today. More, it's become difficult to ship a wheeled unit that will have more capacity, because the wheeled unit obviously need to be able to go on the road, so it's limited in width, in height. So if we need to go more Aether, we'll go with a permanent system. So where we have, we can build plants as big as you can dream it, or we'll have to go with multiple units in parallel. Our mobile unit by default is will treat about 4,500 to 5,000 cubic meter per day at design capacity. But as I said, we can use less, we can go more, we can go 2 lines in parallel. Like the second case study, it was 2 lines parallel. So there you go to your 5,000.
Great.
Go ahead.
In just to keep in essence of our time, we'll do one more question here for it. So what's the most efficient way to remove sodium chloride?
Sodium chloride is very, very difficult to remove in remediation projects. Brine, anything that is soluble, all the sodium, potassium, lithium chloride, all those, magnesium chloride, calcium chloride, all those chlorides actually are extremely soluble, cannot be removed using any of the technology I presented today. If you need to remove that, you're probably looking at the combination of reverse osmosis with evaporation. Not sure how practical this is for a mobile treatment system. It can be done. Reverse osmosis, especially we have wheel unit, but evaporation system for a mobile treatment for a remediation site, that would become to be fairly complex to set up. But basically, if you're talking about soluble salts, nitrates, by the way, are the same thing. Nitrates, chlorides, some sulfates like magnesium and sodium sulfate as an example. All those salts cannot be precipitated. So you're looking at probably membrane reverse osmosis to concentrate, and then if you're close to the sea, you can look at sea discharge. Some clients actually are close to the sea, so sea discharge, especially if it's a brine like sodium chloride and sodium sulfate, this is a major component, the seawater, so it's not really a big deal. So it's possible. Obviously, you need to control metals and make sure you're not discharging something else, but that's possible. Otherwise, deep well injection is also a possibility. I know it's used extensively out west. It's not used that much east, which is kind of weird, but anyway, that's a different topic there. Otherwise, reverse osmosis, and then you truck the stuff, and then you do an evaporation. And you're talking a lot of money on the table there. That's going to be expensive.
Great, thanks, Mark. I believe we've run over our allotted time today. So with that, we'll conclude the webinar. But I do want to remind you, we do ask kindly if you will please fill out the survey at the conclusion of today's webinar. It should take no more than 1 minute, probably 30 seconds, if that. And for those of you that do fill that out, you will be entered to win a $25 gift card. So we will follow up directly with you if you are the winner. And then I do apologize if we did not get to your question today. We will follow up directly with you as well. And then one last thing to note, if you do have any other questions that come to mind that you think of a little bit later, feel free to reach out to Mark as well, and he will get back to you as well for that. It's mark.laliberte@veolia.com. And with that, that will conclude our webinar for today. Thank you guys very much.
So thank you very much.